So now, without further ado, a quick rundown of Rob's pretty impressive CV, and I'm probably forgetting a lot. Most of you will know him because he's very active in the type level community. He works for the Gemini Observatory, which has 2 telescopes, one in Hawaii and one in Chile. He lives in Portland, and he created a functional database library that perhaps people here know, which is called DoBe. And he's a big proponent of declarative and functional style programming, which is ironic because, as some of you may have seen on the slide before this one, is that he once created a set of, I would say he once committed a crime that lets you write Scala as basic, and it didn't even use macros. It used implicits and operator overloading and all kinds of crimes. So it is my big pleasure, and please give a warm applause to Rob Norris.
Okay, thanks everybody for coming. So we're up against another really good talk that's going on the other side. So if what I'm talking about doesn't interest you, or it's too easy or too hard or whatever, feel free to move over. Out of respect for your time, I'm just going to do what I had planned to do. I may run a little bit over, but I'm not going to try and fill up the time. And then if people have questions and want to talk about other stuff, I'm happy to do it. Or you can take off and do whatever you want. Go to the toy shop or something. So my glasses have a defect. I can either see you or my computer, so I'm going to take my glasses off. So before we get started, if you don't mind admitting it, how many of you have used either Scala Z or CATS? So a fair number? Okay. Have any of you actually used DoBe before? A handful? Okay. Wow, awesome. Okay, so this is ostensibly a talk about DoBe because that's what John wanted me to talk about, but it's also kind of a talk about something else I'm obsessed about right now, and it's just some odds and ends that I think are interesting, and I hope you find them interesting as well. So what are our goals? Gain intuition about some simple recursive types. So these things seem to be pretty well known in the Haskell community, but they're not that well known in the Scala community, and they're super useful and just really interesting to think about and mess around with. So I want to introduce those things. Learn a little bit about DoBe, which we'll talk about later. So gain some confidence in pushing on code to see what happens. And this is something that I say all the time, and people ask me, what do you mean by that? So I'm going to try and demonstrate the kinds of things that can happen if you just keep pushing and see what pops out. And don't panic, okay? So recursion is always hard, right? If you're just learning functional programming, you're probably struggling with recursion. Everyone who has learned how to do functional programming can remember struggling with recursion and inductive data types. And what we're going to do today is talking about recursion and co-recursion at the type level. And that's going to be something that's new for a lot of you. And if you feel your brain pressing back against you, that's okay. And I'm going to try and go slow and get to these things in a natural way. But if you become confused at this point, feel free to stop me and ask a question. If it's too fast or too slow, just let me know. Okay, so let's talk about a simple recursive data type. So can people read that? I guess there's no point asking. I can't make it bigger. This is a recursive data type for professors, so math professors and their PhD students who also became professors later. So we've got a name and a year just so there's some data. And the students is a list of prof, okay? And down at the bottom we have, if you look very carefully, you'll see that those lines are, the boxes are connected by dotted lines. So it's just a tree structure. Does that make sense to people? what we can represent here? Okay. So the sort of running problem that we're going to talk about is how can we take a structure like this and map it to a relational database? So how can we write these things out? How can we read them back? And how can we manage the transformation? So let's talk about what it's going to look like in a database table. And this is the way you would typically do it. So you'd have a table that has some unique ID. It has columns for the name and for the year. And then you would typically have a reference to the parent. Okay, so in the natural Scala representation, you have a hunk of data, and it has a list that points to its children. But in a database, that relationship is inverted. You have the pointers going in the other direction. So we're going to get to that in a little bit. But the first thing we need to figure out is how we're going to represent the database ID on the Scala side, because we need a representation for that. And here's one possibility. We can just have an int field with an ID. So what's the problem with this representation? Pardon me?
The ID is generated by the database.
Right, the ID is generated by the database, so if you have a new instance, you don't have any reasonable value to assign to that ID. So you have to create some out of band value, -1 or something, which is no good. We like to use types in Scala. So another way you could do it is like this. You could have the ID be an option event. And that kind of works, and you see people doing this. But I think it's a really irritating representation because you really have three cases. You have either you just constructed this thing and you know there's no ID, or you just got it from the database and you know there is an ID, or you're writing code that is traversing the structure and doing computations, and it doesn't care about this database artifact. It just wants the pure data structure. Okay? And having the option there is irritating in all three of those cases. So I don't really like this encoding. So a way we could make it less invasive is to try to externalize it. So we could do something like this. So get rid of the ID and then have a new type that's a pair of an ID and a prof. Okay? But the problem there, well, what is the problem there? Can anyone see it? Yeah, the students don't have an ID, right? So you have to do this, which defeats the purpose because we were trying to get the ID out of the representation, right? We were trying to externalize it. So that doesn't work. So when you have a problem like this, or when I have a problem like this, and I can't figure out what type makes sense to use, I'll just introduce a type parameter. So let's try that. So we'll just say we have some type A, and I'm renaming this. I'm going to call it PropF, and we'll talk about why in a little bit. It's no longer recursive, right? It doesn't have a self-reference. It just has a list of something as its children. And now we can have type aliases, right? We can say a prof is a PropF of PropF, and an ID prof is a pair of an int and a PropF whose children are a pair of int and PropF, right? Does that compile? That does not compile. PropF takes a type argument, right? So that's what you end up with, right? So the types are infinite. So we need a way to represent these types in a finite way. So what if we do this? What if we make the type aliases self-referential? So here we say a prof is a PropF of prof. So it's pointing back to itself, right? You see how I'm attempting to tie the knot there. The same thing, ID prof is a pair of an int and a PropF of ID prof, which again is a pair of an int and the same thing. And does that compile? That does not compile, because type aliases cannot be recursive. But classes can. How about this? So this is the same idea, but we have an intervening case class instead of just a type alias. So a PropF has a value that is a PropF of prof, so it's referencing itself that way, and the ID prof is the same idea. Does that compile? Yes, that compiles, and that works. Okay, so this is cool. We have one representation of our data type, PropF, and depending on how we want to use it, we can say we have this prof type that is just the plain data, And then we have PropF, which is the data where each value is annotated with this ID label. Does that make some amount of sense? Okay, there's a lot of stuff going on, and we'll speed up and slow down, and hopefully we'll get caught back up. So we could just kind of declare victory here and write the rest of our program and be done, and it would work. But this is functional programming, and we like to generalize things. We like to find the abstractions and things. So I'm going to push on this a little bit and see what's going on. So if we look at these two case classes, there's nothing in the implementation of those classes that's specific to PropF. Okay? So we can factor that out. Okay? So we can just take any unary type constructor there. Okay? So you see the change we made just introducing that type argument. But now prof and ID prof take a type argument, so we have to introduce it on the right as well. Okay? So this is the point at which people start to kind of go like that, and we'll try to reel you back in a second. And note also that ID prof doesn't depend on that label being an int. It could be anything, so let's factor that out. And again, we have to introduce the A on the right in the recursive case, in the self-referential case, right? Okay, so what we have here is we got two data types that are completely generic. They're totally polymorphic in their type argument, and they're potentially very useful. We've identified something that we need to do and that solves the problem really well. So when that happens, I always become really suspicious. And this happens to me a lot. I will think that I've done something clever and realize I've just invented something that's already a thing. So I have learned to look and see if these things are real things. And it turns out that they are. These are both very well-known types. So the first one is called fix. And this gives you a fix point for any type constructor f. This gives you a way to represent that infinite type in a finite way. The second one is called Cofree. It does the same thing, but it associates an arbitrary label with each value. Okay? So while we're at it, I'm going to mention another type that's kind of related. I'm not going to tell you what it is. So Cofree is an A and an F. And there's this other type that's an A or an F. Okay, one is an and one is an or. Does anybody know what that last type is? John can't answer. That's called free. That's the free monad. It is a monad if f is a functor. Cofree is a comonad if f is a functor. So in a kind of a hand-wavy way, Cofree gives you a structure with an annotation associated with each value. Free gives you a structure with a label, with the label sort of at the leaves at the end. So you either have another thing you can unfold, or you get to an answer and you get your A, and that's as far as you can go. So it's worth pointing out that the implementations of these things in Scala Z and CATS are much more complicated than this. I mean, if you look at the Haskell definition, it looks just like this. But we have two problems we have to deal with in Scala. So we need to be able to construct these things with arbitrary extent. They could be very, very big or even infinite. So the structure needs to be lazy. You can't evaluate the whole thing out. And you need to be able to traverse it in a way that doesn't blow the stack. It doesn't run out of stack space. So because of laziness and stack safety, the implementations that you see in Scala Z and CATS are quite a bit more complicated than this. However, I think it's a really good exercise to take this super simple definition, like take that super simple definition of free, define flat map on it, and build it out up to the point where you can write a little DSL and an interpreter just like Runar and everybody else has been talking about for the last 2 or 3 years at Scala conferences. You can build up this free to do all of that. Now it'll be finite, it will not be stack safe, but it'll give you a much better understanding of how this stuff works and how the pieces fit together. So I encourage you to do that. Okay, so I want to point out a couple more things before we move on. So the first one is that if you have a fix, you can always get an F out of it. And if you, just by calling unfix. If you have a cofree, you can always get the F out by calling tail. You can't do that with free, right? Because you might not have an F, you might have an A. However, with free, if you have an F, you can always construct the free. If you have an F, you can always construct a fix, but you can't do that with cofree. So the first family where you can always get the F out are called recursive types. And the other family are called co-recursive types. And just on the basis of identifying that distinction, you can abstract out type classes for recursive types and co-recursive types. And just by virtue of doing that, you get this huge just explosion of operations you can perform for free. All of these different folds and unfolds that you can do, and transformations and fusing of operations. And there's a library called Matryoshka that was open sourced by SlamData. It was written largely by Greg Feil. And it is an amazing, it's just an astonishing library. So if you find that you're interested in these things after this talk, please go out and check it out. It's just absolutely amazing. This is all I'm going to say about it. I'm going to give you a link on the last slide so you know where to look for it. Okay. So some of the things I'm going to do later on in the talk, you would get for free if you use Matryoshka, but I'm not going to do that. Okay, so the second thing I want to point out is that cofree and free are both Fixpoint types. They're just special cases of fix. So what you can do is cofree and free are both directly recursive at the type level, right? So cofree has an F of cofree, and free has an F of free. So we can do the same trick we did before. We can just add a type parameter. So we add a B type parameter here. So we have a cofree F and we have a free F. And we see that cofree is just the fixed point of cofree F, and free F is the fixed point or free is the fixed point of free F. Okay, so that's all I'm going to say about it. I just wanted to get it into your head that there are very general things that are going on, and if you can abstract over this general stuff, you can do some really powerful things. Okay, so that's enough about that. So back to our problem. Now that we know about these general types, we can define prof and ID prof trivially. So prof is a fixed point of prof F, and ID prof is cofree of prof F int. Okay, so I may have lost some people at this point, so I want to slow down and just show you how you can construct these values so that kind of bring it back down to earth. Okay, so here's our original recursive data type, okay? That's just the thing on slide 2 that doesn't have any fancy fixed point stuff going on. And we have a value that we've constructed, and we're just constructing the case class instances. Does everybody get that? Yes? No? Okay. Okay, so what does the version with fix look like? Looks exactly the same. Look, it's just the same. All I've done, I have a fix constructor that's around each PropF constructor. And that's it. We're just constructing data. Cofree, same thing, except at each node I introduce an annotation. Okay? So the structure is exactly the same. We can construct these things. We can pattern match on them. It's just data. It's just data. The types are a little bit intimidating, and the names from category theory are super intimidating, but it's just data. There's nothing at all that's scary about this. So try to convince yourself that it's not scary, because really it's not. Okay, so let's do something else. Before I get back to the database problem, I want to do a little bit of programming with these types in a completely pure setting, so we don't have to worry about I/O effects, because that's going to complicate the database stuff a little bit. So let's write some parsers. Okay, so here's our PropF class again. And here's a hunk of data. This is just a big string, and I don't know why the first line is red. So this is sort of a family tree from Poisson down through a couple branches with a bunch of mathematicians and computer scientists and logicians that some of whom you might recognize. And what we're going to do is write a parser that can parse this thing out into our fixed point types. Okay, so here's one. So this is a parser that parses out a fix of prof. I wrote this using a parsing library called Addo. It's just one that I work on, so I know it well. This would look exactly the same with any monadic parsing library. The combinators are different, but the idea is the same. So what do? We take an n that's the indentation that we're looking for right now. So we skip the indentation, we read the name, so we read everything up to the comma, then we skip the comma and anything after, the spaces after it. We read an int, which is the year that the professor got his PhD, and then we discard the new line, and then we call ourselves recursively at an increased indentation to read any professors that are below the one we just read with increased indentation. Okay, so, and that gives us this recursive call gives us a list of fixed PropF, which is what we need to fill in the child slot when we construct the PropF. So if we look at what we're yielding, it's a fix, a PropF, the name that we read, the year we read, and then the list of students that we got recursively. Okay, and that works. So I can call this on our data. I don't get a useful value back. So something I didn't show you is I hacked the toString to just show you the number of children, the number of direct children, because otherwise I can't print anything on my slides. So I should say that this whole presentation is it's a REPL session that's type checked using a tool called TUT, so that just lets you write interactive REPL sessions, and it's really useful for doing slides like this. So all of this code actually does run. So I wrote a routine that prints it out with the right indentation, and I'll draw a fix, and I'm not going to show that to you, it's not interesting. But we see that we did parse the data, and it looks okay. Okay, so we didn't do anything fancy. This is the same way we would work with just any inductive data type if we were parsing it. But we're using the fix point. Okay, let's do something else. So here's the fix parser again. And here's one with Cofree. So this one is parsing a Cofree of PropF, and it's annotated. Each PropF is labeled with a pair of ints that are the starting and ending parse positions. So the first thing I do is I read the parse position before I consume any characters, then I do everything we just did, and then I read the parse position again after all the children have been read. Okay, and now I yield a Cofree. Okay, so if you look at what I'm yielding, it's exactly the same structure as the fix, except I'm adding this label. I'm adding the annotation when I construct it. Again, it works. I get a useless toString. If I print it out, I get something like this. So I get the same tree, but everything's labeled with its parse position. Okay, I think this is really cool. Okay, so our original idea for having this free slot was to deal with the IDs that we got back from the database. But we can use it for anything. Here we're using the exact same model representation, and now we can show a tree with parse positions. And you can see how this could be really, really useful in something like a compiler. Because if you're instead of PropF, you have some AST, then you could annotate it with source positions, with types that have been inferred, with strictness analysis, with whatever you want, and it doesn't infect your AST. It's all entirely off to the side. You get to decide later what you're going to put in that slot that's provided by Cofree. I think this is really, really, really cool. Okay. Is everybody with me at least kind of in principle? Scattered nods? Okay. Okay, so one more thing before we get back to the database problem. So why the F? So when I made prof non-recursive and introduced the type argument, the type parameter, I renamed it as PropF. And that's because it's a functor. You can map over it, okay? And if you follow this pattern, this sort of design that I'm talking about, this will always be the case. The type that you're using will always be a functor, the data type will always be a functor, and this is called a pattern functor. PropF is the pattern functor for prof and for ID prof. The difference between them is just the recursive structure that we're applying to this functor. Okay, so you can look at the implementation of functor here. It's really easy because the A only appears in the students list, and student is already a functor, so you can just delegate to that map operation. So if we look at the bottom, we have a PropF of string, Doesn't mean anything, but it's a valid type and we can construct one. So we have a prof f whose children are foo and bar, and then we can map s to s.length, and then we get back a prof f of int, which also doesn't mean anything at this point. But you see how the map operation is defined, and it makes sense. Okay, but we can do better than that. Prof f is a traversable functor. Okay, this means we can sequence it. So if we have a prof f of g of a, we can turn that into a g of prof f of a if g is an applicative functor. So we can flip those type constructors, which is a really, really useful thing to be able to do. So just skip the implementation, look down at the bottom. So we have a prof f of option int, okay? So each child is an option int. We can call sequence on it, and what we get back is an option of prof f int. So it just flips those type constructors. Now what would have happened if there was a none in that list, then the whole thing would end up being none. That's how it would work for option, okay? So the definition, if you look up, is a little more involved, but it's the same thing. List is a traversable functor, so we're just delegating to traverse on list. And then because the result of that is in this functor G, we have to use map to get inside and create the new copy of the prof f, okay? It's just an implementation detail that if you screwed around with it, that's probably the only way you could get it to compile. Okay, so the thing we defined is called traverse, but the operation that we use down at the bottom is called sequence. So what's the relationship between those two? So it turns out that doing a map and then calling sequence is a really, really common thing to want to do. So we sort of fuse those together and call it traverse. So map f followed by sequence is the same thing as traverse f, okay? And that's just the definition of traverse. So just by equational reasoning, we can get another identity out of it. So FA is the same thing as FA map identity for some functor, and traversable functors are also normal covariant functors. So the functor law tells us we can do the first thing. And then we sequence both sides. They're the same thing, so if we sequence both of them, that'll mean the same thing. But map followed by sequence is traverse. So now we get to the second identity that says FA.sequence is the same thing as FA traverse identity. Okay? So when you're working with traversable functors, it's good to know those two identities, because you can always swap one for the other if one is more convenient than the other. This is kind of a trivial example, but I love it when I can do this and talk about it. So if you're not familiar with traversable functors, I encourage you to learn about them, because you really can't do monadic programming without them in a generic way. You know, like standard library has future.traverse, and that's because standard library doesn't have this abstraction directly. So you can do it for some specific types, like future, but not for types in general. The future and sequences, I think. Okay. All right, let's talk about DoBe. Okay, so DoBe is a pure functional database layer, JDBC layer, I should say. It's very specific to JDBC. It's for Scala. There are no side effects, and what I mean by that is that DoBe programs are values. Everything you're doing when you're writing programs with DoBe is constructing and manipulating data. Okay, and we'll talk a little bit more about that in a second. It is built natively now for Scala Z and for cats. So if you're a cats user and you weren't using it, you can now try it out. This is in the latest snapshot. Okay, it hasn't been released yet. It is a type level project. I'm very proud of that. And I have stickers, so if anybody wants a sticker, find me. So I had 10 slides trying to very quickly explain how DoBe works. And I decided that wasn't enough to explain how it works if you don't understand this sort of pattern with using free monads to make little DSLs and interpreters. And it was kind of useless to have those 10 slides if you did understand it. So what I'm going to do is just go through very, very, very quickly and talk about sort of the executive summary of what DoBe does, and then I don't think it's going to end up mattering, but if I introduce some type that you don't understand, just stop me and ask what I mean. I don't know where I was going. Okay. So here are the ingredients. So there are algebras of operations for all the JDBC types. So that means we have data, we have big ADTs that describe every primitive operation that's provided by JDBC. And strangely, there are exactly 1,000. So this I don't know. So I just counted them the other day. I was surprised. So this gives us our primitives. This lets us say this is some little micro JDBC operation that I want to provide. So that's the building blocks. So we have free monads over those algebras. So we have 16 little languages for these 16 algebras. And this gives us composition. This gives us a way to take these tiny programs and put them together. We can flat map them together because it's a monad, and we can write bigger, more expressive programs. We have lifting operations for taking programs written in these different languages and embedding one inside the other. Okay, so this gives us embedding. This gives us a way to combine programs written in these different contexts. And then we have interpreters into Kleisli arrows for I/O-like types. So this gives us semantics. This gives us meaning. So free monad is just free monads are just structure. They have no operational meaning. So you interpret this into a Kleisli arrow, which is a function from. So for instance, if you have a connection I/O type, you can interpret it into Scala Z I/O, for instance, and you will get a function of type JDBC connection to I/O of something, whatever type you're computing. Okay, and that will work for Scala Z I/O, Scala Z task, Monix task, FS2 task, any type that has a few specific behaviors. This is still very low level, right? This gives us a pure functional way to write JDBC programs, but we don't want to be writing JDBC because it's really low level and it's really irritating. So we can improve on that with some sort of higher level constructors. Okay, so we have typeset versions of all the JDBC operations that return stupid values like ints, right? So if you say, I want to know what the current transaction isolation is. I don't want an int back. I want an enumerated type that I can pattern match on. So we provide those constructors. We have resource-safe constructors for embedded subprograms. So you can say, I have a connection I/O program, and it's doing something that's yielding a prepared statement, and I have a prepared statement program. I can fuse those things together. I can fuse those things together. And I can guarantee resource safety on that prepared statement that I've constructed. I never have to deal with it, so I can't leak it. It gets closed automatically, and so on. We have composite column vector operations and aggregate operations, which means basically if you're dealing with a result set, you can read back a row into some structured type, some case class or an HList or a tuple, any nesting of those types. And then you can gather those results up in lists and vectors and that sort of thing. Something that's new that I'm working on, it's not published yet, is compile time check SQL literals. I've finally been convinced that's a good idea. So we'll see some of that. So all of this stuff is built on the low-level stuff above. Okay, it's the same types. Okay, the only thing it's doing is constructing little sort of pre-built programs that are easier to use. It's the same types. You can mix low-level and high-level stuff together if you want to, and it will work just fine. Okay, there's no like ugly plumbing layer in between. It's the same stuff. Okay, that's all I'm going to say about it. There's a pretty good video that I did last year describing very slowly how all this stuff works. So if you go to the DoBe site or look at the doc, there's a link to it. It's easy to find. Okay. So back to our problem. So recall our PropF type. So what we want to do, this is the first thing we're going to do, is we're going to construct a program that inserts a PropF, ignoring its children for now, and returning the generated ID. Okay? And note that by the type, we know that it can't do anything with the children because it doesn't know what the type is. Let me say a little bit about what this T-SQL thing does. This is a SQL literal. The interpolated things in there all get turned into question marks in the SQL that actually goes to JDBC. It constructs a program that uses the type safe setters to set those values. It's using some syntax that's specific to Postgres, the returning ID, whatever. I think it's specific to Postgres. So that says insert this thing and then return the database generated ID. And then the .unique int says this is an update we're doing. We only expect a single value back, and it's going to be an int. The syntax is checked at compile time. The type mapping for the parameters is checked, as well as the database can do it. And the output type is checked against the metadata coming back from the database that's telling us what the JDBC type is. Okay. And this has type connection IO int. So that's a value. And what that means is when you interpret it and you finally get an IO or a task or something, when you execute it, it's going to go out and it's going to do something that has to do with a JDBC connection. It's talking about things that I could do if I had a JDBC connection. Okay? But it's just a piece of data at this point. It's not doing any side effecting at all. Okay. I'm going to get rid of this PropF definition to make some more room. Okay. So here is a method that constructs a program that inserts a fix of prof and returns an equivalent cofree back that's annotated, that's labeled with the generated IDs. Okay? So we're giving it one tree, it's going out to the database and doing stuff, and it's giving us back an equivalent tree where each thing is annotated with its ID that was generated by the database. So what can we do here? So we get a fix PropF, and then we get an option int, and that's the optional parent ID. So we insert that node. That's the only thing we know how to do with a PropF, and we get back a connection IO of int. So we need to flat map it because we need a connection IO of something else. So so now we can do fp.unfix. That gives us our PropF. We can map that insert tree method again. We can call ourselves recursively. By mapping it. And then we get back a PropF of connection IO. So what does that mean? That is a PropF whose children are programs that insert the subtrees. Okay? But that's not what we want. We need to flip the type constructor, so we call sequence. So it changes a tree of programs into a program that computes a tree. I think that's amazing that you can do that, but it works. Okay? So now we have the two pieces we need. We have the head and the tail, and we can construct the cofree and yield it. Okay? So we know that map followed by sequence is just traverse, so we can simplify that. Okay. Does it work? It works. So we're parsing our data there and just calling unsafe get to get the fix of PropF out. We're constructing this IO program. So we're doing insert tree, which gives us a connection IO. Transact is something I'm not going to talk about. It basically says, I want to associate this thing with this database pool so that when I run it, this connection pool, so that when I run it, this is where the connection is going to come from. And that gives us an IO value. And then I'm flat mapping it into this thing that draws out the cofree tree in the IO monad. And when we run it, we get this back. And the numbers are so high because I've been compiling the slideshow over and over and over, and the numbers just got really high. Okay? I think that's pretty cool. All right, so how do we read this thing back? Okay. So this is interesting. So we're going to construct a program to read a PropF whose students are ints. Okay? So first thing we're going to do is we're going to select the name and the year for that given ID, and then we're going to select the IDs of all the values who have who have the given ID as a parent. Okay, so we're collecting the data, then we're collecting the IDs of all the children. Okay, the first one is going to give us a unique pair of string and int, and the second one is going to give us a list int back. So we can construct that PropF. Okay, so what does this mean? Right, so this is a PropF whose children are database IDs. So this is like we have one node in the graph. And if we try and take a step off the graph, all we get is an ID. We got to go back to the database and do some more work to get the next step that we're going to. Okay, so I'm gonna acknowledge that this is a super inefficient way to do this. Okay, we're doing 2 queries for every node we're reading back. It would be better to read the whole thing back and assemble this graph in memory. That pushes all the complexity to the SQL, and I don't want to talk about SQL today, so I'm going to do it this way. The example code has the efficient version in it, and it's interesting in roughly the same way. I just don't want to talk about SQL today. Okay, so this kind of gives us one level in the tree. Okay, does that make sense? In principle, okay. So what if we wanted like 2 levels in the tree? Well, we have read node that gives us a PropF whose children are ints, and if we just map read node over it again, we will get a PropF whose children are programs that can read those nodes, and we sequence it. We can traverse it. And now we get 2 levels, right? So read node 2 gives us a connection IO of PropF event. That means we get a node from this graph, and we can take a step before we have to go back to the database and get the next thing. So that's kind of interesting. If we want 3, right? So we can generalize this. I think this is pretty cool because you know, if you have something that's more explosive than these little trees, it could be just an arbitrary graph, and this lets us say, okay, this is the one I'm interested in, and I want to be able to take some number of steps away before I have to go back to the database and fetch some more stuff. Okay, maybe in my UI I only need to show a little bit of it at a time. This kind of thing lets you do that, and the fact that you can only do 3 steps before you go back to the database is encoded in the type. When you get the child of this thing out, it's going to be PropF of PropF event. Its children are PropF event. Its children are ints. So the type tracks how far you go. You don't have like all this lazy loading crap like you have with Hibernate. It's very easy to reason about what's going on, which I think is pretty interesting. But instead of having ints at the leaves, what if we had programs at the leaves? So instead of having to construct a new program to go back, we can say, okay, when we get to the end, here's the program, run it, and that'll explode the next bit out. And we can do that. So we can define this type 3 of A, it's connection IO of PropF of PropF of PropF of A, and then we need the fix point of that, because the programs, the children of this thing, the A, is going to be a connection IO that has a 3-level thing, and its children are going to be the same way. So this is the same recursive problem we've seen before. Okay, and this map.map.map is pretty ridiculous. You can actually generalize this. The sample code uses some tricks in the style of shapeless to create a type class that's indexed on a natural number that lets you say, okay, I want to read this thing, and I want 5 levels, and it will construct the correct type for you. So this is boilerplate. You would never do this, but you can abstract over it. Okay. What we really want to do, though, is just read the whole thing back into memory. That's what we were trying to do, so let's talk about that. Okay, ReadTree. So it takes an ID, and it gives us back a Cofree of PropF int. So it takes an ID, and it gives us back the tree where each node is annotated with its ID. So what do we do with the ID? The only thing we know how to do with it is call read node, so let's do that. And that gives us a connection IO. We know we're going to have to go back to the database and do more stuff, so we're going to flat map. So what's that? PI, that is our PropF of int. So we're going to traverse with ReadTree, and that gives us a connection IO of PropF of Cofree or PropF of int. So that's our tail for our Cofree, and then map to construct the Cofree. And that will work. So we know map followed by sequence is traverse. So we can simplify that. Okay, so I want to take a minute and look at this ReadTree method a little more closely as well, and see what we can do with it. So we want to generalize this, so let's factor out read node, because that's specific to our program. So we'll just take any f. So this takes the int and goes to connection IO. But the only thing we're doing with that connection IO is calling flat map and then calling map on it, right? So it could work for any monad, right? So we can factor that out. So we get an m of PropF of int, but the only thing we're doing with the PropF is calling traverse on it, right? So that could work for any traversable functor, okay? And we're not doing anything with the int other than passing it to f, right? So that can be any type, okay? So this is called unfold C. Unfold C is comonadic, or is comonadic, or Cofree co-recursion. It's just a generalized unfold for Cofree. The m is the monadic version of it. Okay, it takes a seed value and kind of feeds it through and continues expanding until there's nothing left. So this is interesting. This is another totally polymorphic, totally generic, very useful function. It actually doesn't exist in Scala Z. It's an oversight, I think. But I want to make the point that it's worth doing this, even if you only call that method one time, okay? Because the more polymorphic your code is, the fewer ways you can write it. And that means the fewer ways you can write it wrong, okay? Sometimes stuff is so polymorphic, there's only one way you can write it that will actually compile. It's not true in this case. But it really limits the possibility that you're going to make a dumb mistake, okay? It limits the number of possible dumb mistakes, we'll put it that way. Okay, so in any case, with this, our ReadTree is trivial. It's just, we just delegate to read node and we're done. Okay, does it work? Well, okay, so because I've been inserting so many copies of this, I had to actually find the newest Hilbert ID because I've done them so many times. So the Hilbert program computes an ID for Hilbert. This IO type, Hilbert flat maps it into ReadTree, associates it with a database. And when we run it and draw it out, we get that little subtree that we inserted for Hilbert before. Okay, so let's review a little bit. So we've learned about some recursive types. And I hope I've convinced you at least a little bit that if you kind of push on things, I don't think we pushed particularly hard, and these types just popped out. Right, and that really happened for me. I did not expect that to happen, okay? And so Fix and Cofree popped out as a natural thing, a natural consequence of the stuff we were trying to encode. It's not a contrived example. It's like a real world thing that we think about. So we use them to do something useful, and a lot of different things, right? We have this one representation for just basic raw tree values. Tree values annotated with database IDs. Tree values annotated with parse positions. Tree values annotated with, what else did we do? We did a lot of stuff. A lot of different representations that we got for free by using a pattern functor and these recursion patterns. We pushed some code around. Not much more to say about that, I guess. I just think it's cool, the kinds of things that you can do with functional programming, with pure data, and with equational reasoning. And this is not like a lot of database programming. I wasn't thinking about connections and closing resources and iterating result sets and stuff like that. I was just like pushing things around and following the types. So I think that's a really powerful thing to be able to do. And hopefully we weren't scared. If this was if this was difficult for you, then good. It was difficult, really difficult for me. It's totally reasonable for it to be difficult. The slides are going to be up. I'm going to give you some links. So look at Matroshka. And Greg Feil has some talks he's given. He has a good repo associated with that. These slides will be up along with sample code. They're not up yet, but they will be, and I'll tweet it if you follow me, or if you don't want to, you can unfollow me as soon as they show up. If you don't want to do that, I'm not trying to get followers. There's a lot of documentation on the DoBe website if you're interested in DoBe. And it's now on Scala exercises, which is awesome. The 47 Degrees guys developed a module to teach DoBe, and it's really cool. It all runs in the browser, and it's really cool. And that's all I've got. Thank you for your time. Any questions? Oh, really? Yes, Tim. Thank you, Tim.
So I'm really curious, when you, I mean, the common thing here is that like, you have an impedance mismatch in lots of domain models between like, okay, I'm going to do a query and get some domain type, and then sometimes you want the domain type in your model, and then sometimes you like need the IDs. Is that what you were doing when you actually figured this out?
Yeah, that's what I was working on. And it's a common question that comes up on. I mean, I get it all the time in DoBe, and I'm sure the slick guys get the same questions. How do I deal with IDs that might be there or they might not be there? And I think this is an interesting solution to that problem. And I'll point out that it works even for types that aren't recursive, right? Anytime I have a field that represents a foreign key, I turn it into a type parameter. And that way, I can have, there are all these different representations. Like I have a list of customers, and I just want like the names and addresses. And then I have a list of customers, and I also want their orders, but I just want the IDs of the orders. Or I want the orders and all of the information associated with them. And just by turning that thing into a type parameter, you get all that. You get all that for free. So it kind of removes a lot of this boilerplate multiple representations that you end up writing. Any other questions? Wow. All right. Well, thanks a lot.